Hello, my name is Xianfeng Wang. It's my great honor to give a talk in Season 2 of the Geometric Analysis Seminar. I would like to thank Huju for inviting me to give a talk here. Today, I will talk about self-similar solutions to fully nonlinear curvature flows by high powers of curvature. This talk is based on joint work with Dr. Sanze Gao in Shanxi Normal University and Professor Haizhong Li in Tsinghua University. There are two parts in my talk. In the first part, I will review some background about contracting curvature flows and self-similar solutions, which will be presented from three aspects: mean curvature flow and self-sinkers, flow by homogeneous of degree 1 functions, and the resolution of the generalized Firey conjecture. In the second part, we will present our main result. Before we show our main theorem, I will first review some other important results on self-similar solutions which are not included in the first part. Then we will present our main theorem and also the sketch of the proof. Now let's start from the background. Let N be a smooth Riemann manifold and M be a smooth hypersurface of N. We consider the contracting curvature flow, which is given by a smooth family of emulsions, satisfying the following evolution equation. On the right-hand side of the equation, it is minus f to the power alpha nu. Here alpha is a positive constant, nu is a unit outward normal, and f is a smooth function of the metric and the Wingard matrix, which is invariant under the change of the coordinates, so we can also regard it as a smooth function of the principal curvatures lambda I of the hypersurface MT. Usually, the function f is assumed to satisfy the following basic properties. We call it condition 1. Lambda lies in gamma, which is an open symmetric and convex cone in Rn. F is smooth, symmetric, and positive on gamma. F is strictly increasing each argument. This will guarantee that the flow is a strictly parabolic flow, so that we can apply the theory of parabolic equations to obtain the regularity of the flow. Finally, F is assumed to be homogeneous of degree 1. This is because that we have already put the power alpha in the flow equation. The most famous contracting curvature flow is the mean curvature flow, which corresponds to the case f equals the mean curvature, alpha equals 1. So it is a homogeneous of degree 1 flow. This kind of flow was first introduced by a physical scientist Mullins. He introduced mean curvature flow to describe the behavior of green boundaries in annealing pure metal. Also, from a geometric point of view, we know that the mean curvature vector appears naturally in the variation of the area functional. So, from the formula, we can see that mean curvature flow is a greater flow for the area functional. So it is a very natural geometric flow. Also, in 1978, Bloch studied the mean curvature flow from the viewpoint of geometric Meyer theory. In 1984, Huiskin studied the mean curvature flow from the point of view of geometric analysis, which has a very deep influence on the study of geometric flows of hypersurfaces. The main result of Huiskin's paper in 1984 can be stated as follows. If n is at least 2 and the initial hypersurface M0 is closed and strictly convex, then the solution MT of the mean curvature flow converges smoothly to a round point P as T tends to the maximum existence time capital T, which is finite. So it has two meanings. First, the flow will contract to point in finite time. Second, the flow will become more and more round, and Huiskin obtained a very precise description of this behavior. If we assume capital T is the maximum existence time of the mean curvature flow with initial strictly convex hypersurface, and assume that MT tends to a point P, we can move the origin to P and then rescale the hypersurface to obtain a new family of hypersurface MT tilde. Then the rescaled hypersurface MT tilde will tend to a sphere with radius square root of n. This is a famous result of Professor Huiskin. We can also understand the Huiskin result by comparing the flow with the Swinton spheres. Since mean curvature flow is a extrinsic curvature flow, so it only depends on the principal curvatures of the hypersurfaces, which implies that the mean curvature flow will preserve the symmetry of the hypersurfaces. So if the initial hypersurface is a sphere, then at each time it is still a sphere. Then the mean curvature equation reduces to an ordinary differential equation, and we can solve the ordinary equation immediately. Finally, we find that the radius RT is given by square root of R0 square minus 2nt. So from the solution, we find that if t tends to R0 square over 2n, then the radius will tend to 0. It means that the sphere swings to a point. So then Huiskin's theorem means that the asymptotical behavior of the strictly convex hypersurfaces and the mean curvature flow is modeled by swinging spheres. Huiskin's result is about the hypersurfaces with dimension at least 2. For the one-dimension case, it is usually called curve shortening flow. There are also some famous results. The first one is due to Gaussian and Hamilton. They prove that if M0 is a convex embedded curve in R2, then the solution MT on mean curvature flow converges smoothly to a round point in finite time. Later, Gaussian showed that the convex condition in Gaussian and Hamilton's result can be dropped. Gaussian proves that if the initial curve M0 is an embedded curve, not necessarily convex, then the solution of the mean curvature flow will converge to a convex curve in finite time. Then, by applying Gaussian and Hamilton result, the curve will finally converge smoothly to a round point P at t tends to a maximum existence time. So this results about a compact case. In the complete non-compact case, there is also an important result by Cao and Zhu in 1998. They proved that if M0 is locally Lipschitz completely properly embedded curve that divides the plane into two regions of infinite area, then the solution of the mean curvature flow exists for all time, and for each time t, the curve MT has similar property with the initial curve. That is, each MT is smooth, complete, and properly embedded curve which divides the plane into two regions of infinite area. This is a complete non-compact case. For mean curvature flow, there is a interesting phenomenon concerning the type 1 finite time singularity. In 1984, Huiskin proved that if M is compact, then the mean curvature flow has a smooth solution on maximum time interval between 0 and capital T, which is finite. And as T tends to capital T, the maximum of the norm square of the second Fourier form tends infinity. Moreover, Huiskin later proved that the supremum of the norm of the second Fourier form times capital T minus T to the power of 1 over 2 has a positive lower bound 1 over 2. In this paper, he defined a type 1 singularity by the condition that the supremum of this function is finite. And if the supremum of this function is infinite, then we can call it type 2 finite time singularity. And in this paper, Huiskin focused on the type 1 finite singularity. In the paper mentioned before, Huiskin proved a very famous and important monotonicity formula. And by applying this formula, he showed that solutions of mean curvature flow forming a type 1 singularity can be homogeneously rescaled, such that any resulting limited hypersurface is a self-sinker. Here I present some important formulas here. So without generality, we can assume that the orange is a blow-up point, and we can rescale the hypersurfaces to obtain a new family of hypersurfaces at x tilde, and we can also define a new time variable st. From the definition, we can immediately see that if t tends to capital T, then s will tend to infinity. We also define a function, the tilde x. Then, by applying Huiskin's monotonicity formula, we see the evolution equation for the integration of rho tilde over m s tilde. So if we do integration according to s from 0 to infinity, then the left-hand side must be finite. So it implies that the right-hand side has to be finite too. So which means that as t tends to infinity, the function, the norm square of the mean curvature vector plus the normal part of the position vector must be 0. So it means that if we have a type 1 singularity of mean curvature flow, then by rescaling the hypersurface, we can get a spatial self-sinker. So this is the relation with type 1 finite singularity of mean curvature flow and self-sinker. Generally, we can also define self-sinker for submanifold. We call a submanifold in the Euclidean space a self-sinker if it satisfies the cosilinear elliptic system given by equation 1. The left-hand side is the mean curvature vector, and the right-hand side is minus the normal part of the position vector, which comes naturally from the asymptotical behavior of the type 1 finite singularity. On the right-hand side, if we have a self-sinker, then we can also rescale the self-sinker by adding a factor, a square root of 2 times capital T minus T. In this way, we obtain a new family of hypersurfaces which only depends on the time t. So we can compute the evolution of the hypersurfaces easily and check that it satisfies the mean curvature equation. So we get a spatial solution for mean curvature equation. Also, A self-sinker also have some close relation with minimal submanifold. In fact, X is a self-sinker is equivalent to that M is a minimal submanifold of the Euclidean space with the conformal metric Gij. It is also equivalent to that M is a critical point of the weighted area function F. So we can also apply the technique and methods of minimal submanifolds to study the self-sinkers. Now we review some classification results for self-sinkers. When n equals 1, p equals 1, and the curve is closed, average and longer give a complete classification. So now we call these curves average longer curves, and the only simple closed one is a circle. Every average longer curve has very good symmetry. When n is at least 2 and p equals 1, which can prove that spheres are the only compact and mean convex self-sinkers. Here mean convex means that the mean curvature is non-negative. So this is about the compact case. For the complete non-compact case, Hodgson gave a very complete classification for self-similar solutions for mean curvature flow with n equals 1 and p equals 1. He studied not only the self-sinkers but also the self-expanders and the translators and so on. Also, in 1993, Huisken considered the complete and non-complete case for self-sinkers. He proved that if the self-sinker is mean convex and has polynomial volume growth and has bounded second volume form, then the self-sinker must be the hyperplane or generalized cylinder or the remaining product of the average longer curve and hyperplane. Later, in the famous paper of Cody and Minicozzi, where they introduced the notion of F-suitability to study the singularity of mean curvature flow. In this paper, one of the results implies that Huisken's result is still true without the boundedness of the second fundamental form. Smolik generalized Huisken's results from hypersurface case to higher co-dimension case. And Professor Haizhong Li and Yong Wei, they later proved that smoothest result is still true under a much weaker condition. And there are also some other results not listed here. Now we look at the definition of self-similar solutions to contracting curvature flows, which is inspired by the definition of self-sinkers. We call that the contracting curvature flow is a family of smooth emulsions satisfying the following evolution equation, and F is assumed to satisfy a basic condition 1. Then we call a hypersurface in Euclidean space a self-similar solution to the flow 2 if it satisfies the following equation. The left-hand side is a speed function f to the power alpha. The right-hand side is the normal projection of the vector of the position vector. Similar to the self-sinker case for mean curvature flow, if we have a self-similar solution of the flow 2, then we can obtain a family of hypersurfaces by adding a time factor alpha plus 1 times capital T minus t to the power of 1 over alpha plus 1. And this family of hypersurfaces satisfies the contracting curvature flow too. So in this way, we get a special solution of the flow. This is one of the reasons we call it self-similar solution. Now we look at the flow by homogeneous of degree 1 functions. Roughly speaking, Huiskin's results in 1984 have now been extended to a very large family of homogeneous of degree 1 curvature flows. We denote by gamma plus the positive cone, which is a domain with all the variables xi positive. Professor Bennett Qiao proved that if the speed function is given by the Gauss curvature to the power of 1 over n, then the behavior of the flow is similar to the mean curvature flow as Huiskin's result in 1984. Later, in 1987, Professor Bennett Qiao showed that if the function is given by square root of the scalar curvature with an initial pinching assumption, the conclusion is there too. That means that the flow has a similar behavior with the mean curvature flow for strictly convex hypersurfaces. This flow had attracted lots of attention. One of the reasons is that the flow is not only an extrinsic flow because R is an extrinsic geometry curvature, and it is also an extrinsic geometric flow because by Gauss equation we know that the scalar curvature is a constant times the sigma 2 curvature. In a series of papers, Professor Banyos proved that Huiskin's result is still true for some other kinds of homogeneous of degree 1 functions. Professor Banyos considered lots of classes of functions. Here I list 4 of them. The first one is the surface case. In this case, Professor Andrews do not assume any additional condition for f except that f satisfies the basic condition 1. The second case, f is convex. The third case, f is concave and f is 0 on the boundary of the positive cone. The fourth case, f is concave and inverse concave. Here, inverse concave means that the function f star is concave. In particular, the square root of the scalar curvature satisfies the fourth condition. So it means that Professor Bennett Qiao's result is true without a pinching assumption if we apply Professor Benyo's result. Also, Andrews, McCoy, and Zheng, they also consider some other kinds of speed functions. Here I list just one case, that is, f is inverse concave and f star tends to 0 as the variable tends to the boundary of the positive cone. There are lots of functions which are concave or inverse concave. The simplest one is the mean curvature function, which is concave and inverse concave. Also, there is a function named par means. If the p is less than or equal to 1, then f is concave. If p is larger or equal to minus 1, then f is inverse concave. Also, if we consider the case elementary function of the principal curvature, that is sigma k function, then the functions given by sigma k plus 1 over sigma k are given by sigma k to the power of 1 over k, or sigma k over sigma l to the power of 1 over k minus l. All of these functions are both concave and inverse concave. So we have lots of examples, and we also produce new examples by considering the convex combinations and some other kinds of combinations. Now we look at the self-similar solutions to flows by one homogeneous functions. I view some results by Professor James McCoy obtained in 2011. The first one can be stated as follows. if M is a closed hypersurface satisfying the self-similar equation, where F satisfies condition 1, and if F is concave or F is convex and M has non-negative mean curvature, then M must be a round sphere. The second one, if Fm is a closed, strictly convex hypersurface satisfying the self-similar equation, F satisfies the condition 1 and is inverse concave, then M must be a round sphere. And McCoy also considered some other cases. Now we look at the resolution of the generalized Firey conjecture. The general picture for arbitrary contracting curvature flows is far from being well understood except the flows by powers of Gauss curvature, with power larger than 1 over n plus 2 or equal to 1 over n plus 2. This kind of flow was firstly studied by Firey in 1974, where Firey used this flow to describe the motion of the rolling stones. Firey made the ideal assumption, that is, he assumed that the stone has uniform density and is worn with uniform frequency in all directions. So this means that the stone is worn in the direction P, the rate of the worn in the direction of P is proportional to the limit of the area of the Gauss image m omega over the original image s omega as omega times P. We know that if the region omega tends to P, then the limit tends to the Gauss curvature. So it means that it is reasonable to use the Gauss curvature flow to describe the motion of rolling stones. And Firey conjecture that the convex surfaces will become spherical in finite time under the Gauss curvature flow. This conjecture was finally solved by Professor Benjos in 1999. And in 1996, Professor Benjos considered the other kind of flow by powers of Gauss curvature with power given by 1 over n plus 2. This flow has a very special geometric meaning because the right-hand side is just the affine normal. Professor Benjos proved that this flow converges to an ellipsoid in finite time, and he proposed a generalized Firey conjecture. That is, he conjectured that if the power alpha is larger than 1 over n plus 2, then the flow will converge to round spheres in finite time. In 2002, Andrews and Chen considered the surface case. They showed that if alpha lies between 1 over 2 to 1, then the generalized Firey conjecture is 2. And Andrews and Lee considered the case for n at least 3 and with initial hypersurface axially symmetric. They proved that under this condition, the generalized Firey conjecture is 2 for alpha lying between 1 over n and 1 over n minus 1. Finally, the generalized Firey conjecture was solved by combining two important theorems. The first theorem can be stated as follows. Convex hypersurfaces in Euclidean space contracting under K alpha with alpha larger than 1 over n plus 2 converge to a smooth, uniformly convex self-similar solution of the flow. after scaling to a fixed volume. This theorem is due to Professor Benio's for alpha lying between 1 over n plus 2 and 1 over n, and it is due to Professor Guanpengfei and Nilei with alpha equals 1. And finally, Professor Benio's and Guanpengfei and Nilei considered all the case for alpha lying in 1 between 1 plus 1 over n plus 2 and infinity. The second theorem was proved by Professor Bender, Qiao, and Daskalopoulos in 2017. They showed that the self-similar solution of the Gauss curvature flow of the flow by pairs of Gauss curvature with pair larger than 1 over n plus 2 must be round spheres. So combine the two theorems, the generalized Firey conjecture is finally solved. From the resolution of this conjecture, we can also see that the self-similar solution of the curvature flow play a very important role.